Hello. In this video lecture, we're going to discuss confidence interval, part 1. The outline is, first we discuss statistical estimation in general, and then we'll discuss several very specific confidence intervals, including confidence interval for one sample with a continuous outcome, confidence interval for one sample with a dichotomous outcome, and confidence interval for two independent samples with a continuous outcome. Okay, now statistic estimation. Okay, statistic estimation is the procedure to compute an estimate of a population parameter from a sample. Okay, a parameter is a population attribute, and its value is usually unknown. For example, if we are interested in knowing what is the prevalence of HIV in the United States, so that's a population attribute, and we don't know. And the only way we can get an estimate is by collecting a representative sample and then use the sample data to estimate the prevalence. So if we have one sample, we can get one estimate we call a point estimate. So a point estimate is one numerical statistic for estimating a parameter based on sample data. So just one number. And the procedure or formula for computing an estimate from sample data is called an estimator. So it can be a procedure or can be a formula. Okay. So here on the right-hand side, you can see a few estimators. For example, the sample mean is an estimator of the population mean. The sample variance is an estimator of the population variance. The sample proportion is an estimator of the population proportion. So once we have an statistical estimator, we wonder how good it is, and we want to evaluate it. And we usually use bias and precision to evaluate how good a statistical estimator is. So if you look on the right-hand side, there are 4 situations. The one on the upper left, this is unbiased and precise. And this is what we are hoping for. We want to look for estimators like this. Okay. And the one on the upper right, it is precise because the points are not all over the place. They're pretty much focused, but it's biased. It's away from the center, which is the true value of the parameter. And the lower left indicates it's no bias. It's unbiased, but it's not precise because the points are scattered all over the place. They're not precise. And the lower right is what we really try to avoid. It's both biased and not precise. Okay. So I think the entire statistical estimation theory is try to reduce bias while maintaining precision when we create good statistical estimators. Okay, now we must say a point estimate does not reflect the uncertainty or the variability in the data. So what we mean by that is we know we cannot know the true value of the parameter because we don't have access to the entire population. So we rely on the representative sample to create a point estimate. But if we select another sample, we will be able to generate another estimate. So if you draw many different samples, then you get many different estimates. So to assess the variability in the data in estimation, then we must depend on the sampling distribution, which is the distribution of the estimate when we select the different random samples. Okay. So that's how we take into account of the variability in the data. In order to account for the uncertainty in the data for statistical estimation, we usually compute something called the standard errors or margin of error from the sampling distribution, and using those to compute the confidence interval. So the confidence interval is really a tool for us to do statistical estimation and take into account of the uncertainty in the data. So a confidence interval is a range of possible values that may contain the true parameter value with certain probability. And this certain probability is also called the level of confidence. Okay. Here's a few examples of margin of error. So the first one is, you can see, actually the first and second one are the margin of error formulas for estimating a binomial proportion. And the last one is the margin of error for computing a t confidence interval for a population mean. Once we have a confidence interval, how do we interpret what it means? Okay, so a confidence interval is a formula for computing the upper and the lower limit from sample data and a specified confidence level. So what does that mean? So in the Rice Statistics Simulation Lab, you can find this simulator. Basically, you can determine how many samples you want to draw from the population and use the confidence interval formula to compute a confidence interval. Basically, a 95% confidence interval for the population mean mu may be interpreted as if we use the CI formula to compute 100 intervals based on 100 random samples, then about 95 of the intervals should contain the true value mu. Okay, this assumes we have a good confidence interval, we have a good estimator. Okay. All right. Now we want to discuss some specific confidence interval. The first is we want to have a confidence interval for a one sample mean. Okay, and we assume the standard deviation sigma of the population is known. If we have that, then we can use the z interval if the data is normally distributed, and the formula is listed on the right hand side. Okay, but this is a very good textbook example because the assumption of the population standard deviation sigma is known is really not true in most of the situations in the real world applications. Okay, so we often have the situation when the standard deviation sigma is unknown, so we have to take into account how to estimate sigma as well. And then we have the one sample t confidence interval for the one sample mean. But when can we use that? If the data is normally distributed and the sample size is less than 30, then we should use the t interval. And if n is greater than 30, then we can still use the z interval, but replace sigma with the sample standard deviation s. And the table 6.3 on page 104 represent the formula for that confidence interval. If the data is not normally distributed and n is less than 30, then we should use non-parametric methods. Okay, so this outlines when you can use the one sample t-test. Basically, these results are based on the central limit theorem. So basically, if we have non-normally distributed data and the sample size is small, we should consider non-parametric methods. Otherwise, we can rely on the t interval or the z interval. And to compute the z or the t confidence interval for one sample mean, of course, we can manually perform the calculation using the formulas, but we can also use SPSS one sample t-test module. And I have provided a link. It has detailed information about how to do that. Basically, you go compare means and analyze, compare means, and one sample t-test. And this is really, this works for when you have the raw data. Okay, it's not summarized data into sample means and sample standard deviations. You have the raw data, you can perform a one sample t-test, and the one sample t-interval will be a byproduct. And confidence interval for one sample with a dichotomous outcome, the formula is listed on the right-hand side, as well as table 6.6. Basically, it's a z-interval because we have used an approximation to the binomial distribution by a normal distribution. And there are some assumptions or prerequisites for using this method. Please review those assumptions in table 6.6. And these assumptions are to guarantee that discrete distribution can be approximated well by a normal distribution. Without these conditions, this confidence interval will not be accurate. And then we have the confidence interval for one sample dichotomous outcome. We can use the formula, but also we can use SPSS using the information shown in this website. So it involves the non-parametric, legacy dialogues, and binomial distribution, and then you need to specify some values for the SPSS to calculate the interval for you. Okay, and I'm going to provide another step-by-step instruction and a video for doing this. Confidence interval for two independent samples of a continuous outcome. And the formula for the confidence interval for the difference of two population means based on independent samples is shown on the right, as well as in table 6.8 on page 105. So you can see on the right-hand side, it uses the difference of the sample means and the z-score, and then there's the estimate for the sample variance. So it's a pooled estimate from the sample variances of the two samples. And keep in mind that this formula works well when either sample size is large or the data follow normal distributions. And of course, you can use SPSS to actually compute these confidence interval for two independent samples by performing a independent sample t-test. So analyze, compare means, independent sample t-test. And of course, this works for raw data with the raw observations. And if you have summarized the data like sample mean, sample variances, you can use the formula to manually compute the confidence interval. And I will provide another step-by-step instruction and a video on how to perform this computation.